Okay, so now I'm gonna start sharing my screen. We're gonna start out with problems from Cracking the Coding Interview, this book, and then we'll go as we'll see how it goes. So the first thing I wanted to do is talk about just briefly touch on the concept of time complexity. So what I want first of all is a show of hands about people who are, if not comfortable, at least familiar with the concept of time and space complexity. Cool. So I'll just give a brief introduction of complexity analysis for our beginners and people who have not taken CS1 and CS2. First of all, complexity analysis is a very, very important concept. And I can demonstrate this later after some problems that we do. Basically, the problem was historically in computer science that you had all these people coming up with different approaches or different problem solving techniques, but you didn't know which one was better than the other unless you actually measured the time that it takes for specific standardized sets, and that was really a problem. The great Donald Knuth came up with the idea of or big O notation, or time complexity analysis. The idea, forget the history lesson here. The idea here is that take the sorting problem, for example. If you're given a list of randomly arranged numbers and you want to sort it 1, 2, 3, 4, 5, how do you do it? So there's a bunch of ways to do it. One of them is the BOGO sort. BOGO sort literally means you just kind of randomly arrange the numbers and then check if the list is sorted. If not, then you just randomly arrange it again and check if it's sorted. Now that's obviously a terrible solution. A much better solution is something called insertion sort, which is something called an n-square sort. There's also n log n sorts like merge sort and quick sort. And there's also linear sorting algorithms, which you don't really need to know for coding interviews, but they'll cover that in CS2. So the idea of complexity analysis is that there are some algorithms that are inherently faster than other algorithms, and this is how you describe them. So if something is O of n, it's better than something that's O of n squared because it takes less time. So you want to, the goal is to come up with algorithms that take less time and less space. Space is also, it's the same thing, you just, instead of time, you do space analysis. I will go over this more in detail later. This was just to briefly touch on it because I will be addressing this sometimes, and it's good to just get a little introduction out of the way. So with that being said, I am going to share my screen and we are going to start, talking about problems. So let me know if you can see this screen that has Eclipse on it.
Yep, I can see it.
Awesome. So you can see I have a bunch of projects here. So we're going to look at arrays and strings project here, and I've already done a bunch of problems, but let's just make up a new project. New project. It's going to be a Java project. Wait, hold on, it's much easier for me to do it this way. Okay, don't create module. I can talk about that later as well. So we're going to make a class. So the first problem we're going to solve is the first problem in the arrays and strings chapter in Cracking the Coding Interview. It's called is unique. And oops, one sec. And I'll get to LeetCode in a little while. So I've written the problem description here. So I'll just use this problem description, and you guys can already see the solution, so sorry for that. Here, so here's the problem description. Implement an algorithm to check if the string has all unique characters. What if you can't use additional data structures? So for now, let's just ignore this extra problem. And Cracking the Coding Interview is a great book, in my opinion, because it has this really nice concept called BCR. It's called the best conceivable runtime, and it really, really helps you in coding interviews. So the first thing is the problem is to check if the string has more than has all unique characters. So which means that you actually have to touch each element in the string at least once. You have to check it against other elements in order to do so. And well, in that case, you cannot possibly do better than O of n. So here we have one approach or solution that I have written down. Like use a hash set. I can talk about it in a little, but one potential solution that I have written down, a brute force solution, but it's one solution. So you have string str equals ABB. Okay, so one possible solution is that you take A and you compare it against every other character. If there is no collision, then you don't do anything. But if there is a collision, then you return false. So how would you do that? Well, let's write a method. Public static boolean. I'm gonna call it check. So we're gonna write a for loop. Sorry. Okay, so the idea is, method. The idea is what we're doing now is we're gonna, we've picked char is s dot char at I. Okay, so now we're gonna run another loop. And it's gonna start at I because we don't want it to collide with itself, because if it collides with itself, it's always gonna find a collision. So it's gonna be less than s dot length, and then we're gonna do j plus plus. And if c equals s dot char at j, then we're gonna return false. And then otherwise we're gonna return. So this is a very simple solution, but it's bad because it's bad because we're literally going through the same thing twice. Well, how can we improve it? But first, let's see if it works. So it should return false, which it did. And let's say if we replace this B with C, just return true. So this behaves as expected. But the problem is that we're already checking, we're doing something called we're checking twice. We're going, so complexity analysis wise, you're going through the string once. And for every character in the string that you go through once, you're going through the whole string again. So this is something called an O of n square solution. And obviously we don't like this because it's more time than necessary. But at the very least, the first thing you've done is that you have a solution working. So in Cracking the Coding interview, she talks about how you should first talk about the brute force solution. The reason is because there are some candidates who can't even figure out the brute force solution. So you show that you at least can do that much. And once you've done that much, then you can think about other techniques or other solutions. So we have this O of n square solution down pat. By the way, does everyone understand how this works? All good, no problem. Want to make text size a tad. Oh, I'm so sorry. Does this work? Okay, so now let's look at other conceivable solutions. So here I have written down a solution, which is using a hash set. So what is a hash set? Well, first of all, let's talk about what a mathematical set is. A set is basically just an unordered collection of items. An array, on the other hand, is an ordered collection of items. And what's important about sets is because they're not ordered, you can't have duplicates of the same kind. Think about mathematical sets and Venn diagrams. If you have a set that has 1, 2, 3, and you put 1 inside it again, you're not going to put 1, 1, 2, 3. It's just 1, 2, 3 again. It's the same concept here in a hash set. The hash word comes from a hash table, which I'll talk more about in a later lecture. But a hash table really allows you to do, or hash table, hash set, hash map, allow you to do lookup, which is in order one time. So a hash map is literally mapping a key to a value. A hash set, on the other hand, just hashes the element that you're trying to hash by according to some hash algorithms. And the reason they're good is because they have amortized runtimes of OO1. Now, what does that mean? It means that when you try to look something up, this isn't going to take extra operation time. So let's say that in here, I'm doing a hash up. I'm doing an array, like I'm traversing through an array, or I'm traversing through a linked list, which I'll talk about more in detail later. Linked lists are, if you want to find something on a linked list, it's an O of n operation. So that means that you're doing this, which is n, and within each, for each n, you're doing this one, which is also n. And then for the linked list, you're also doing an n operation. Even if it's in a different method, you're still doing the operation, which is now the complexity gets worse. It's n cubed. So really the cool thing about hashes is the complexity doesn't get worse because it's amortized OO1 runtime. What do I mean by when I say amortized? Amortized literally just means on average that its runtime is O of 1. And I can talk about, when I talk about hash maps and hash tables, I can address the cases where it's not O of 1. So let's come up with a hash solution. So public static Boolean.
So what would be the space complexity
Of what?
for your brute force solution?
For my brute force solution? Well, if you consider that this isn't, okay. Thank you for reminding me. So one good practice to do is to keep these temp variables that you declare outside the scope. It's just like, it's just better to do it that way, better standard programming practice. But the space complexity would be O of 1 because the only extra thing you're using is this temp char c variable. But you actually don't even have to use this. So if I take this out, I just put it for convenience. But if I take this out and I just put s dot char at I, the solution works the same. The space complexity for this is excluding the string, which you don't count in space complexity. The space complexity is O of 1 or constant because you're not really, and actually in this case, it's actually 0 because you're not making any other extra variable other than I and j. So it's constant space complexity. It doesn't matter if you were A, B, C, D, E, F, G, or if you were A, B, C, or A, just A. The amount of variables that you're making, the extra stuff that you need, is always constant. That is why the space complexity is constant. It's similar to how, let's say I design a phony algorithm, which always returns true, no matter what it's given. It doesn't do much. But the runtime for this is constant because it's always going to return 1, and doesn't matter what you give it to it. It doesn't matter what you give it. It's always going to return the same thing. And it's not going to, it's not O of 1 because of a consequence of returning the same thing. It's O of 1 because it doesn't do anything. It doesn't, it recurs to the string. So no matter if the string I gave it was empty, it would still do the same thing. And if I gave it like a 1,000 character string, it would still do the same thing. Does that kind of make sense?
Yeah, it's pretty clear. So if it's like any size of a string regardless, it's always constant.
In this case, yes, for this phony algorithm. Now, if you actually like say iterate through the string, then that's going to be O of n. So like in this case, you're iterating through the string once, but for each time for each element in the string, you're iterating through the whole string again. So it's going to be n times n, which is n squared. Now, I want to ask you guys a question. So if I take this out somehow, if I'm able to make this, and just kind of like put this here, would this still be n squared? Yes. Ryan says yes. What about other people? Would it still be n squared? Okay, Albert says nah. Albert, do you want to explain why you think that?
Yeah, okay. You took that inner loop and you put outside the outer loop, right? That's okay, yeah. So basically when you iterate like that, you're no longer doing it, each time you iterate an outer loop, you're no longer doing another n operations. Instead, now it's 2n, which goes down to n really, because you're just doing it once, you're doing it another time.
Right. So Albert brings up an important
time.
point, which is that in this case, you're iterating for every element. Every time you go for every I, you're going through all possible J's. On the other hand, in this case, if I somehow took this out and put it outside, assume that I did, you're doing I and J independently or separately. Just imagine that we didn't have I in the thing itself. So that would be N. I would take N, and then this would take another, like, let's just take this outside. This would be N, this would be an O of N thing, and this would be an O of N thing. So you're adding the two up, which is O of 2N. But the beauty about O of a big order or big O notation is that you never really care about constants. So you just kind of like throw the two out and it's still O of N. It's still a linear time solution. And the reason for that is because you care about scalability. Like you want to see by having a bigger string, how much does my algorithm scale? So in this, for an n square, it grows at a square, like this place of a square. On the other hand, on a linear algorithm, it grows as a linear. It doesn't matter what your constant multiplication is, it still grows linearly. And that's really the crux of the idea behind big O notation. So let's look at this. Let's look at this hash set solution. So what are we talking about here? So first of all, let me talk about what a hash set is. I already told you what, I already told you what a set was. Was that clear? So what's cool about this is that in Eclipse, you can press Control-Shift-O and it already, like using Vim commands, it just imports whatever libraries you're having. So, but before I do that, I want to ask the one beginner that we had. So you have experience in C, right? Okay. So Ryan, like, do you kind of understand what we're doing here, even though this is Java? Oh, cool. Okay, awesome. So in that case, yeah, I was worried over nothing. Thank you, Ryan. So basically, we have this hash set that we're going to store characters in. Now, what we're going to do is we're going to go make a for loop. Oopsie. You know what? I'm just going to copy this. We're going to make a for loop that iterates through every element of the string. So what, can anyone tell me what order operation this is? So this is an order. Yeah, no worries, no worries. This is an order n operation because you're going through every element in the string and you're just putting it in the set. Now, as I said, if you guys remember, I said that what's cool about hash sets is that well, adding and like just doing the thing, it's an amortized order one thing. So like you're literally just putting it all in a set. And now what's cool is now that we're done with this pre-processing, we can literally just, if we have a conflict, we can just say, hey, there was a conflict. So now I'm going to if set.contains s.char I, then we have a conflict because the set already has it. And we're going to return false. Otherwise, I mean, I don't really even need to put this else because if it meets this condition, it just exits out of this hash set. But otherwise, it's just going to add it to the set. And we're going to return, if it hasn't returned false yet, it's going to return a true. So this is, this should be an order n solution, which is infinitely better than order n square solution. Just by adding this little thing called the hash set, we've made this better. And one sec, what is the problem? Oopsie, my bad. We've already made it better. And like, what if there's a conflict, CBC? It's going to return false. Does this make sense to everybody? Do you understand the solution? Okay, awesome. So now the cracking the coding interview lady says, so by the way, this hash set solution is my own. It wasn't in the cracking the coding interview, but I was looking at what she was saying, and she was saying that what if your interviewer asks you, can you make this better? So according to our BCR that we analyzed, you can't really make it better in terms of runtime because it's already O of n. You can't really have a better runtime than that, since you always need to touch each element in the string at least once. So what else can you improve? Well, can we improve the space complexity? So Andrew asked me the question about space complexity earlier. Can you look at the space complexity here? Andrew, what do you think of the space complexity in this case?
Well, since it's a hash set, is it always going to be constant?
Well, in a hash set, the time complexity will be constant. However, the space complexity, since you're adding n elements to each to the set, you're going to have.
Oh, it varies by the string, right?
Yeah. So it's going to be O of n, the space complexity, because you're adding each character of the string to the hash set, either until it breaks, or if it doesn't break, then you actually do add every element of the string to the hash set. So it is an O of n space complexity. So can you make this better? Can you make it a constant space complexity? And I would argue that the answer is no. But then I looked at what they said, and it's like if you're using Unicode or ASCII character sets, those are limited by the amount of characters you can enter to it. And hence, you can argue that the space complexity is never going to exceed whatever amount of character sets number of characters the character sets have, in which case the space complexity is constant. I think that's a fair argument because you don't have infinite number of variations you can put. At the most, it's going to be 192 characters, whatever characters ASCII has. In which case, yes, the space complexity is already constant in our solution. I know it's a hacky solution, but if you ever encounter this in an interview, then this will be a cool flex to make. So this was a good problem. Is everyone comfortable with it?
For the is unique for the hash solution, would you recommend in like an interview if they asked if you can make it O1, leaving it as a hash set, or would you say that like to make it clear that it's constant, like changing the hash set into like an array or something, you know, like might be, because I know that like the value of the s.char@, you could get like a consistent value of what the actual ASCII or whatever it is value is, and then you could like index on your array like that. Like I don't know if that's like, because I was just asking if like you could make the argument that the hash set would be O1 space, or if you should try to switch it to an array and like check the array, you know what I mean, or something like, or some kind of solution like that.
I understand what you mean. So let me. I think that's a very good question for people who didn't understand what he was talking about. So I think Dylan, correct me if I didn't understand you correctly. But what Dylan was saying, that if we have a constant, if we have an array, you guys are you guys familiar with the concept of frequency arrays?
Okay. Can you reiterate, I guess, like a quick overview of frequency array?
Okay, so a frequency array is basically just, let's say that you're solving a problem with strings. You're given a string and you want to see if those, you're given two strings and you want to see if they're like anagrams. Do you remember what an anagram is, Andrew?
Like race car or?
No, it's just a permutation of each other. Like if the characters in, so if you take Java and the string Vaja are anagrams of each other because the number of characters and the characters are the same. They're just arranged differently. So that's an anagram. So what he's saying is, so how you can use frequency arrays is that you literally just, for like, there's a space allotted for J, and each time you see a J character, you just increment the number in the frequency array by 1. And basically, I think what Dylan is saying is that you have a fixed frequency array for the whole ASCII character set. And then just every time you encounter one, you just like increment it by 1. And if there's if it's not been seen, and if already been seen, then you return a false. Is that do I understand you correctly, Dylan?
Yeah, I was just wondering if that would be like, if that'd be worth explaining. Like, you know what I mean?
I
Like
mean,
in
you
an
can
interview.
explain it, but if you if I can tell you how hash sets work or hash tables work. So a hash set is just a set implementation of a hash table. A hash table is literally, if I can see if I can draw here somewhere. Give me a second. Sorry. A hash set is, or a hash table is literally just a bunch. It's just an array kind of, and and it's indexed by its hash value. So let me turn off the background and I can show you what I am talking about. Stop sharing and choose virtual background. This two screen thing is very confusing sometimes. Can you see me without the background?
Yes.
Okay, so this is a very crude diagram, but basically what it is that this, imagine this is your hash table. This is your hash table, okay? And each time you want to insert an element in it, like each one of these have indices. And let's say that you want to insert some like 4 into it, okay? So 4, you run a hash function on the 4, and then you store it, whatever value you get. You store it in that value, you kind of like index it. And there's something called, like, there's different implementations. There's different ways of dealing with conflicts. One of them is called a chain conflict. You're gonna learn this in CS1, or at least I did. So when you have too many conflicts, a lot of them are just put in the same thing. So lookup for here becomes an O of n operation, or O of whatever's in that thing operation. But if the hash function is written well, which the hash function in Java is written very well because it's written by experts, you're not going to have that many conflicts, which means that your lookup time or your insertion time is going to be constant, which means that when your time is constant, you're basically doing the same thing as your frequency array idea. The hash set is basically just a formalized version of your frequency idea in this case. Does that make sense?
Yeah, totally. Thanks for
Thanks
for the diagram.
Cool, no problem. Ryan asked me, what is the O of n solution without the data structure? So Ryan, there is no O of n solution without an extra data structure. Well, one thing you could do is what Dylan's idea is, have an array that you've already initialized, but without unreasonable restrictions. There is no O of n solution, because in that case, the best solution would be just to do the n² solution. I'm sorry if the answer is a little unsatisfying, but when you have to, like, if you look at the GCR, you have to have an extra data structure, because otherwise you can't you can't do lookups in O of 1. And there's many data structures that allow you to do lookups in O of 1, and my favorite one is the hash table, which is, implementations are hash set and hash map. So I hope this answers your question. With that being said, are we good to move on to the next problem? Okay, awesome. So now I thought, so there's a few problems. So the first, I was thinking about, in the interest of time, I will go and do palindrome permutations. But we can also look at check permutation. So let me read out the two problems for you, or actually, let me just pull them up. So here's palindrome permutation. The question basically just asks, given a string, is a permutation, check if a given string is permutation of a palindrome. So everyone here familiar with the concept of what a palindrome is?
So if you rearrange the letters, or not rearrange, but if you read
That's an anagram.
Not read it, yeah. But the race card I was referring to before is a palindrome. So if you read it's the same thing from left to right or right to left for the word, then it's the same word.
Exactly. So let's look at this simple one. So 1, 2, 2, 1 is a palindrome, because if you somehow, like, imagine this is a mirror, then you've mirrored it. It's the same thing. The same thing for race car. If you imagine that this little character is a mirror somehow, then race car's mirror would be just a race car. Those are palindromes. And you're asked to do a problem in which you're given a string. You don't know if it's a palindrome or not. What you want to check is if it's a permutation of a palindrome. So this is one problem that we could do. And the other one we could do is given two strings, it's check permutation. Given two strings, let me just minimize the solution. Given two strings, check if one is a permutation of the other. I actually like this one because I was asked, actually asked this question in an interview, not worded exactly the same, but it was a very closely worded. And I had never seen the problem before that. So one of the things I want to try and develop here is the ability to think on your feet, that if you see encounter a problem that you've never seen ever before in your life, then how are you? That's what they want to test in interviews. So which one do we want to do? What I'm going to do is I'm going to set up a GitHub repository, and I'm going to put all this code. So if you ever want to have answers to these problems, then you can always go look there. Okay, I'm just going to assume that everyone wants to see check permutations, which is the one I saw in an interview. So the question is, given two strings, check if they're permutations of each other. And I can give you guys an example. So you're like, one simple one is Java and Raja. Like, are they permutations of each other? Yes, because their characters are like the number of characters and the characters are the same. They've just been rearranged. Another one permutation is this one, and like, all of these are permutations of each other. So intuitively, how would we solve this? Like, if this is the first time you've seen this problem, somebody asks you out of the blue in an interview to solve this problem, how would you do it? Let's look at the BCR. What is the best conceivable runtime that you can do it in? Well, given that you have to touch all the elements in both strings at least once, it's going to be at least O of n plus O, and O of n1 plus O plus n2, where n1 is the size of the first string and n2 is the size of the second string. That is, conceivably, intuitively, you can't think of a better, there's no way that you can come up with a better solution. So, I mean, this is very helpful to have the BCR, because now you know what do you do. So one solution could be that you generate every possible permutation. Of one string, and then check it against whether it's the same as the other one. Does this work? Yes, it works. Is it bad? Yes, it's very bad. And the reason is because if you generate every permutation of something, let's think about how many permutations there are. So, there's like for 1, 2, 3, how many different arrangements are there? Or there's going to be 1, 2, 3, then 3, 2, 1, another 1, 3, 2. Then there's going to be 2, 3, 2, 1, 3, 2, 3, 1, and then 3, 1, 2, and 3, 2, 1. So there's six possible permutations for these. And then, like, God forbid you put like 10 elements. That's going to be 10 factorial, and that's a lot. So the the complexity for this one is time complexity for this one is going to be n factorial, which is insane. This is a lot. You don't need to generate every permutation possible. By the way, I will talk about a permutation algorithm where you can generate every permutation, but you don't need to do that here. If we look at the properties of the two strings, we know that they all have to have the same elements. So one other possible solution could be that you go through each string, you go through each one string, and for every character, you try to match it to another character. So you'd have something constituting of 2 for loops. Okay, so for string 1, every character in string 1, You go through every character in string 2 and try to match it. And then you'd have to have some sort of like a used array to say, oh, I've already used this one, so you can't have this one. You can't reuse this element for the same thing. So if you don't have that, then if you're looking for, if your two strings are these two, then they would look the same to the computer because you're not keeping track of frequency. But so anyone want to time complexity analyze that kind of approach?
So is that the approach where, yeah, sorry, is that like the one where you have permutations? You find all the possible permutations every time and see if they contain one of the permutations?
So that is the that is not that one. The time complexity for that is n factorial. The one I'm talking about is when you match every character of the string with every other character. So you have two for loops nested into each other. Do you want to think about the time complexity for that one? Correct, Ryan. More specifically, yes, you're correct, but more specifically, it's going to be n1 times n2 because you're going through. And I mean, you're correct. I'm not going to nitpick here, but yes, you are right. It's less bad because it's infinitely better than n factorial, but can we do better? And this is the best solution I came up with. This is the throw everything, go through one string, throw everything into a hash table using frequencies. The key is the character and the value is the frequency. And then go through the second string and keep subtracting from each one. So let's code this up, okay? I wanted to get to some LeetCode problems, but that seems unlikely, but that's fine. I hope we can, I'm going to put all this code with explanations anyways. So, oh, I would recommend you guys learn common Vim commands because those are really, really useful when typing quickly. So you have string 1. We're going to use the same example, Java versus and what I'm going to do is we're going to build a solution. So public static boolean. Can I call them A and B instead? I feel like that will be easier. Okay, so what we're going to make is a hash map. We're going to map each character to an integer. See, that was so many typos. Cool. Let's okay, cool. So now what we're going to do is we're going to go through each character in string 1. So int I equals 0. And I plus plus. And then for every character, what we're going to do is if the map has already seen it, of course, it's when you start out, the map has nothing, so it's not seen nothing, so it's not going to go to this. But contains key, map dot contains key, then a dot char at I. So if it has seen it, then we just update the frequency. So map dot replace, and we're gonna we're gonna replace each value that it's already seen, and we're just gonna update the frequency. So my fingers cooperate with me here. I will So a dot get, a dot, oh right, we're not doing this. It's going to be map.get, and it's going to be, and this is why I usually like to store everything in a temporary variable, because then you don't have to type as much. And the consequence, since it's linear space, I mean constant space, it doesn't really matter. So if it has seen it, it's gonna update the frequency by 1. There's that 1. Otherwise, so sorry about me being very nitpicky about the format that I like to do things in, but that is just how I am. We're just going to put, we've seen it once. If it's not there, then we've seen it once. So what this has done is, this is a linear operation. So the time complexity for this is O of n1, and space complexity is also O of n1. But what we've done is, now we've made it easy to look up every character of string A, and we can do that in constant time. That really saves a lot of time for us to do other things. So now we're going to go through the other string. So we're going to go through int I equals 0, I is less than b dot length, I plus plus. Then, so if map dot contains key, and then we're going to do b dot char at I, and then we're good to go. But the problem is if the map doesn't contain it. So we're going to return a not here. We're going to put a not character here. So if it doesn't contain this, then we're just going to return false. You already know that there's one character in there that is not contained in our map. That should be, so that by extension, there's a character in string B that is not in string A. So therefore, we should return a false. But if we've already seen it, one second, we've already seen it, then we're gonna do this replace operation again. So we've seen it, we're gonna subtract 1 from the frequency array. It's gonna be b dot I. And if it goes through everything somehow, then we're gonna return true. So let's test out Java and Waja. So test out, I'm gonna check S1, S2. Let's see what happens. This should return a true. And lo and behold, it returns a true. But now let's do a runtime analysis on this. So this operation did O of n1 time, and this operation did O of n2 time. So the overall operation, this doesn't take any extra space. I mean, any extra linear space. I mean, we have these two, but this one, but I mean, that's just constant. So the entire algorithm as a whole will take O of n1 plus O plus n2 space, or time, and O of n2, n1 space. Okay. So some optimizations. The first thing you can do, and you can talk about this, is if a dot length is not equal to b dot length, sorry, 1 minute. So this one doesn't really optimize time. Cool. Thank you for coming, Dylan. I think I'm gonna stop now too. But this optimization doesn't really optimize time. All it does is optimizes space. So we've already eliminated a lot of the cases before we even actually store anything. So that is the reason why. I should test this, by the way. So what if we have all the characters are the same, just the frequencies are different? What happens then? Still returns false. Awesome. Does this make sense, everyone? Okay, awesome. Cool. So feel free to reach out to me if you have any questions. I'm willing to do one-on-one tutoring. I'm always happy to help as many people as I can. But I'm going to set up a GitHub repo very soon. I recommend checking this book out because there's only so many interviews or so many problems that I can do in front of you. But what really helps think on your feet and what really helps you become a better programmer and better interviewer is when you practice the stuff yourself. So normally what I would do is I would offer to do, like, after this session, I would offer that if you guys want to stick around and practice more problems, then I can do that. But unfortunately, today is Diwali and I have some family events going on. But starting next week, I will be able to offer that. Thank you so much for coming, everyone. Harold, I will send you the recording as soon as I get it. Thank you. Bye-bye.